Hello, welcome to my video on data structures. This is part 4 of the array data structure, and we will be discussing the implementations of the operations that we have introduced. In the previous videos, we have introduced several data access and data management operations. We have introduced fundamental operations such as data access, insertion, and deletion. Some other operations are just special cases of these primary operations. For example, accessing the first or the last element are special cases for the generic data access operation. We have also introduced some auxiliary operations for memory management, such as accessing and changing the capacity or the size of the array. In this video, we will implement each of these operations using C++. For the implementation, I will try to prioritize code simplicity rather than runtime efficiency. I will also try to use less C++ features, so if you are not familiar with it, you can still get the key ideas. Let's begin with naming the operations. We name the generic data access operation at, the operation that accesses the first element front, and the one that accesses the last element back. Then we call the generic data insertion operation insert, and the generic data deletion operation erase. There are special cases that operate on the last element are called pushback and popback, respectively. Finally, for the memory management operations, we call the capacity and size access operation capacity and size, respectively, and the capacity and size modification operations are called reserve and resize, respectively. Since some of the fundamental operations, such as insertion, depend on the memory management operations, we will first implement the memory management operations before the data access, insertion, and deletion operations. Let's begin with the internal storage of the data. We have 3 major variables. The first one, also the most important one, is the set of continuous memory blocks we used to hold the data elements. We call it items here. Note that it has a type, data type, which allows our array to hold any data type such as integers, floats, or characters. If you're interested, you are welcome to dive into the notion of template in C++. Otherwise, you can simply replace data type with int and assume that we are only dealing with a set of integer numbers. The remaining 2 variables, the size and the capacity, are simply used for recording the corresponding values. Their data type is size t, which is similar to the unsigned integer type in C++. It means that these variables cannot be negative. Let's begin with the capacity access operation. Since we have used a variable to store its value, we can simply return the variable the capacity. The keyword const here means that we do not expect the function to modify any variable. Similarly, we simply return the size for the size access operation. Let's move on to the capacity modification operation reserve. The function takes in one parameter new capacity, which is the amount of memory blocks it needs to allocate. At line 4, we compare the new capacity with the existing capacity. We know that we only need to request for more memory if the memory we need is more than the memory we have. In this case, we will only proceed if the condition is met. Now, if we need to proceed, we will request for more space at line 6. If you are not familiar with C++, you just need to know that the keyword new is used to request memory. The address of the new place with more memory is then returned to temp. After that, we will use a for loop to move all existing data from the old place, items, to the new place, temp. The keyword move is also a C++ feature that can make the process faster by actually moving the data instead of copying the data. But you can simply treat it as a variable assignment if you're not interested in the details. Finally, in line 11, we will swap the address of the items and temp, and the new place temp now becomes the existing place that holds the data elements. Okay, now consider the size change operation resize. The operation takes one parameter, new size, which is the size of the array we wish to change into. In line 3, we are checking whether the new size of the array exceeds its capacity. If yes, we would call the reserve operation to allocate more memory in line 6. Note that we would ask for twice as much as the new size to reduce the frequency of memory reallocation. Now, let's move on to the fundamental operations. Let's begin with the data access operation at. The function has one parameter index, which is the index of the data element we are accessing. The implementation depends on whether you want to perform out-of-range error checking. That is, whether the index we give as input is out of the range of the array. If you do not care about error checking, you can simply return the value of the data element using the square bracket operator in line 5. On the other hand, you will need to compare the index with the size of the array. If the index is smaller, then the access is within the bound and we can return the corresponding value. Otherwise, in line 9, we throw an error message to notify the error. If you want to know more about C++ error notification, you can read more about the keywords try, throw, and catch. The next one is the data insertion operation. It has two parameters. The first one, RHS, or right-hand side, is the data element we want to insert. Again, you can think of it as an integer when we are dealing with integer array. The second parameter, index, is the location of the array where we want to insert the new data element. In line 4, we will increase the size of the array and make sure it is ready to hold the new data element. Then, in line 6, we check whether we need to move any data element. Note that the size of the array has been increased by 1 after calling the resize function at line 4. Therefore, the new size will need to be at least 2 if the old array contains at least one element. If that's the case, we will then use the code block from line 8 to 10 to move forward all data elements after the insertion index by one memory block. And after that, we place the new data element to its designated location in the array in line 13. Then, let's talk about the data deletion operation erase. The function has one parameter index that identifies the data element to be deleted. Similar to the data access operation add, the code shown here includes error checking. We begin with checking whether the index of the data to be deleted is out of range in line 3. If no, we use the code block from line 5 to 8 to move backward all data elements after the index by one memory block. In this case, the data element to be deleted is overwritten by its next neighbor. Also, remember to decrease the size of the array by 1 in line 9. In cases where the bound checking failed, we issue the error message in line 12. Finally, let's talk about the operations that are special cases of the previous ones. Here, we show the implementations of front and back, which access the first and the last element of the array, respectively. As you see, these operations can be performed by calling the more generic data access operation at. We just need to supply the proper index. Similarly, operations pushback and popback can also be implemented using the generic data insertion and deletion operations. For pushback, we simply call insert by specifying its index to be the end of the array. And we also call erase to implement the popback operation. You may notice that the indexes we use for pushback and popback differ by 1. This is because for pushback, we are actually appending the new data after the last data element of the array. But for popback, we are actually deleting the last data element. In this case, one index should point to the position after the last data element, and one should just point to the last data element. And that's why they differ by 1. Alright, in this video, we have demonstrated the implementations of all array operations we have discussed so far. In the next video, we are going to implement another operation which merges two arrays. In addition, we will also test our implementations to see if they perform as expected. Okay, that's the end of this video. See you next time.